Welcome to the deep dive. Our mission today is really clear, super focused. We're doing a rapid but deep run through of the essential concepts from Unit 2.
That's right, the living world, biodiversity, ecology.
Exactly. We want to make sure you are absolutely ready for your test. We're hitting the most critical points you need to know, and fast.
Right, so Unit 1 was kind of the foundation, right? The biogeochemical cycles, the nuts and bolts.
Yeah.
Unit 2 is where it really pivots. It's all about how organisms interact, where they thrive, what limits them.
So moving from just the cycles to the actual species and their lives.
Yeah, and ecological relevance, biodiversity loss, and, well, the huge impact humans have on all these systems. Often negative, unfortunately.
Okay, let's unpack this then. If we're looking at the health of life on Earth, we got to start with counting, right? You need to know those two main ways ecologists measure diversity. What are they?
Okay, so they look at it from two angles. First is species richness. That's basically just the list. How many different species are there in that place?
Just the total number. Got it.
The second one, and this one maybe tells you more, is species evenness.
Evenness. Okay, how does that work?
It's about proportionality. Like, are the populations of those different species roughly equal? Or is one species totally dominating?
So richness is the variety, but evenness is how balanced that variety is.
Exactly. The fairness of the distribution, you could say. It's easy to mix them up.
Right. Give us that classic example that shows why evenness is so important.
Okay, think about the Arctic tundra. Let's say you go out, you count 100 animals, and you find they belong to 3 different species.
Okay, 3 species. That sounds pretty low for richness.
It is a little richness. But now look closer at the numbers. What if 90 of those 100 animals are wolves? And the other 10 animals are split between, say, Arctic foxes and hares.
So richness is 3, but wow, it's basically the wolf show. The whole ecosystem is tilted towards one species.
Exactly. That really high dominance, that low evenness, it suggests the system might not be very resilient. It might look okay on paper with 3 species, but it's potentially fragile.
Fragile. Okay.
And that's why ecologists often combine both richness and evenness into indices. Like the Shannon's index is a common one.
And that gives a more complete picture of health.
Right. A system with high richness but super low evenness, like our wolf example, is considered much less healthy or stable than one where all the species have sort of similar population sizes. It shows structural integrity or lack thereof.
Got it. Structural integrity. So, okay, where does nature usually achieve the highest richness? The sources point to 2 main factors.
Yeah, it really boils down to time and location. You find the most species richness in old places.
Old places, like geologically old.
Yeah, land masses that have been stable for ages, billions of years sometimes, going way back to Pangea. That gives evolution a really long time to work.
Okay, time. And the second factor?
Location. Specifically places close to the equator. Latitude 0, the tropics. That's where richness peaks.
Okay, old and tropical. And the flip side is also key for the test. Where is diversity naturally low?
It's lowest in geologically new land, or land that's been, recently reset.
Like volcanoes.
Exactly. Brand new volcanic islands like Hawaii popping up from the ocean floor.
Yeah.
Or land that's just been uncovered by melting glaciers up north.
Right. There hasn't been enough time for many species to evolve there or even get there.
Exactly. Nothing's had time to colonize or adapt yet.
Which brings us neatly to how species do get to these new places. This is the theory of island biogeography, right? E.O. Wilson's big idea.
That's the one.
And for you listening, understanding how islands get ranked by diversity based on size and distance, that's crucial.
Right. The theory basically says organisms get to islands by, well, swimming, floating, maybe flying.
Okay.
And the number of species an island can eventually support is this balance, this equilibrium between new species arriving in migration and species already there going extinct.
And distance affects immigration, size affects extinction.
You got it. Closer islands get more arrivals. Bigger islands can support more species and have lower extinction rates.
So let's rank them. If you have 4 islands, hypothetical islands, where do you find the most diversity?
Okay, number 1, the highest diversity is always going to be on the big islands that are close to the mainland.
Makes sense. Easy to get to, lots of room.
Exactly. Low extinction, high immigration. Now, after that, it gets a bit more nuanced. The next tier down is kind of a tie or close to it.
Okay.
You've got big islands that are farther away.
So the size helps make up for the distance.
Right. Or you have small islands that are closer in.
Where being close helps make up for the small size. Okay, almost a tie.
Pretty much. They often have similar diversity levels, but the absolute lowest diversity, the most isolated, most vulnerable places.
Let me guess. Small and far.
Small islands, far from the mainland. Nailed it. Think places like the Galapagos, or some really remote Pacific islands. High extinction risk because they're small, and very low immigration because they're so far out.
Like a Hawaii too, right? Very far.
Hawaii fits that category.
And didn't Wilson do that wild experiment in the Florida Keys to prove this? Fumigating islands?
He did. It's a classic study. They basically tented these small mangrove islands and killed all the insects and arthropods, sterilized them.
Wow. And then watched what happened.
And then they watched. They meticulously tracked how quickly bugs recolonized from the mainland and nearby islands.
And it matched the theory. Closer islands got repopulated faster.
Perfectly. It showed proximity was key for rapid recolonization. He even documented things like spiders ballooning on silk threads and, yeah, the famous example of a rat apparently floating over on some debris, maybe styrofoam.
A rat on styrofoam. That really shows how even non-flyers can get there if it's close enough.
It demonstrated that size and distance aren't just abstract ideas. They are real governing factors for life on islands.
Okay, so every organism is sort of pushing outwards, trying to reach its full potential, its ecological niche, but reality, like island distance, always pushes back.
Exactly. And that leads us perfectly into the difference between a fundamental niche and a realized niche.
Right. Fundamental is the dream.
Pretty much. The fundamental niche is the absolute full range of conditions, physical, chemical, biological, sol, that a species could theoretically tolerate and use if there was zero competition, zero predators, none of that.
The absolute ideal world for that species, but that's not reality.
No. Reality is the realized niche.
Yeah.
That's the actual slice of the fundamental niche the species ends up using because of interactions with other species.
Like competition.
Competition is a huge factor. The classic example is barnacles on coastal rocks.
Ah, yeah. Tell us about the barnacles.
Okay, so you might have one type of barnacle that could live all over the intertidal zone. That's its fundamental niche.
Top to bottom.
Right, but maybe there's another slightly tougher bluish barnacle that outcompetes it in the upper zone, where it gets dried out less.
Okay.
So the first barnacle species gets pushed out of the upper zone and can only survive in the lower, wetter zone. That lower zone becomes its realized niche. It's smaller than the fundamental niche purely because of that competition.
That's the competitive exclusion principle, basically, one species pushing another out.
Exactly.
And this stays right into ecological tolerance, doesn't it? The limits of what an organism can even handle, environment-wise.
Absolutely. Competition might shrink your niche, but tolerance defines if you can even live there at all. Ecological tolerance is that limit, the range of conditions, temperature, water, salinity, whatever an individual or a whole species can handle before, well, things go bad.
Before damage or death.
Right. And you can visualize this with the range of tolerance graph. It usually looks like a bell curve.
Okay, walk us through the zones on that curve. These seem important for the test.
Definitely. Right in the middle, the peak of the curve, that's the optimum range. That's where the species is happiest, healthiest, reproduces best. Paradise.
Got it. Thriving.
Then, as conditions move away from that sweet spot, maybe it gets a bit too hot, or a bit too cold, or too salty, you enter the zone of physiological stress.
Stress zone. So, not dead, but not happy either.
Exactly. The organism is struggling. It might be growing slower, not reproducing, maybe it's slowly dying, but it's not instantly lethal. You mentioned the Bakersfield kids at the beach example.
Right, 68 degrees Fahrenheit feels freezing to them. They're miserable, complaining.
But they're surviving. That's physiological stress. They're outside their optimum temperature range.
Okay. And if conditions get even worse, past the stress zone.
Then you hit the wall. That's the zone of intolerance. Beyond that point, the conditions are just too extreme. The organism's basic physiological processes like enzymes working or just metabolism, they fail. Death occurs.
That's the hard limit, the law of limiting factors again?
Precisely. Whatever factor pushes it into intolerance first is the limiting factor.
And this idea of tolerance range, this curve, it also explains the difference between generalists and specialists, right?
Perfectly. Think about the width of that bell curve. Generalists like raccoons, coyotes, rats, they have a really broad tolerance curve.
They can eat almost anything, live almost anywhere.
Right. They thrive when conditions are unstable or changing because they're adaptable. They have lots of options.
Okay. And specialists.
Specialists, like the giant panda needing its specific bamboo, or maybe a koala needing certain eucalyptus, They have a very narrow tolerance curve.
Super picky.
Very picky. They can be incredibly successful and outcompete generalists in very stable environments where their specific needs are perfectly met.
But if that one thing changes...
Exactly. If their specific food source disappears, or the temperature shifts just slightly outside their narrow optimum, boom, they're immediately in the zone of physiological stress and heading towards intolerance really fast, much less adaptable.
Okay, so that's individuals and species. What happens if a whole ecosystem gets knocked way outside its tolerance, like a huge disaster? How does it recover? That's ecological succession.
Right. And the key thing to remember for succession, the absolute decider between the two types, is one simple word: soil.
Soil. Okay. How does that work?
Well, we talk about two main recovery paths after a disturbance. If the recovery has to start from absolute scratch, with no soil left at all, that's primary succession.
No soil. What kind of disaster wipes out the soil completely?
Think really catastrophic stuff. A massive volcanic eruption that covers everything in lava or ash.
Okay, like rock.
Yeah, brand new rock. Or huge geological shifts, landslides maybe. Or the big human one. Paving over huge areas with concrete or asphalt, you've removed all soil.
Right. So how does life even start again?
It needs pioneer species. Things like lichens, maybe some mosses. These amazing organisms can actually live on bare rock.
And they make the soil.
Slowly. Very, very slowly. They secrete acids that break down the rock, and when they die, their organic matter mixes with the rock dust. It takes an incredibly long time. The sources mention it could take something like 100,000 years for solid granite in Yosemite to turn into usable soil through this process.
Wow, 100,000 years. Primary succession is seriously slow.
Painfully slow.
Yeah.
But what if the disaster doesn't remove the soil?
Then it's faster.
Much faster. That's secondary succession. This happens when the disturbance removes the existing community. Maybe a forest fire burns the trees, or a flood washes things away, or a farmer abandons a field.
But the soil is still there underneath.
Exactly. The soil is intact.
Yeah.
And crucially, that soil often contains nutrients, dormant seeds, spores, roots. The biological legacy is still there.
So it doesn't have to start from bare rock.
Nope. Seeds sprout, plants regrow from roots. Since that foundation is already laid, recovery is way quicker. You can get a forest back in decades or maybe a century or two, not hundreds of thousands of years.
Okay, primary versus secondary, all about the soil. Got it. Now let's zoom out a bit to the really big fundamental rules governing all this, the conservation of matter and energy.
Yes. These are bedrock principles, and they can be kind of counterintuitive.
How so?
Well, our everyday experience makes it seem like things just disappear. You throw
Okay.
something away, it's gone. You burn something, it vanishes.
Right. Out of sight, out of mind.
But that's the myth we absolutely have to bust for the test. Matter is conserved. It cannot be created or destroyed, only changed in form.
So when people dumped waste into rivers, like the Thames historically, or pesticides run off fields, it didn't actually disappear.
Not at all. It might dissolve, get diluted, spread out, change chemically, but the actual atoms are all still there, somewhere in the system. The total mass is conserved.
Okay, that makes sense. Now tell me that car exhaust example again, because that one really messes with your intuition.
It really does. Okay, so you put, say, 10 gallons of gasoline in your tank. You drive until it's empty. Does the exhaust coming out of your tailpipe weigh less than, the same as, or more than the gasoline you put in?
Intuitively, you'd think less, right? You burned it up.
That's what most people think. But the answer is the exhaust weighs more.
More. How?
Because of conservation of matter. Gasoline is mostly carbon and hydrogen atoms. When it burns, those atoms combine with oxygen atoms from the air.
Ah, the oxygen adds mass.
Exactly. The carbon combines with oxygen to make CO2. The hydrogen combines with oxygen to make H2O, water vapor. You're adding the mass of all that oxygen from the air to the original mass of the gasoline. So the total mass of the products, exhaust, has to equal the total mass of the reactants. Gasoline plus oxygen. It gets heavier.
Wow. Okay, that really drives home the conservation of matter point. And energy is conserved too, right? It doesn't disappear either.
Correct. Same principle. Different law, first law of thermodynamics. Energy cannot be created or destroyed, only converted from one form to another.
So when I burn a log in the fireplace, the heat doesn't just vanish when the fire goes out.
Nope. The chemical energy stored in the wood is converted mostly into heat and light energy. That heat energy warms the room, warms the chimney, eventually warms the air outside, and just spreads out, dissipates across the whole planet. It doesn't disappear, it just becomes less concentrated, more dispersed. That's entropy, the second law, in action too.
Spreading out. Okay. And the coastal temperature example fits here too.
Perfectly. Think about a hot, sunny day. The same amount of solar energy is hitting a beach on the coast and an inland area, like Bakersfield.
Right, same sun.
But the coast stays much cooler. Why? Does the energy disappear at the beach?
No, based on what you just said. So the ocean must be doing something with it.
Exactly. The ocean absorbs a massive amount of that heat energy. But instead of just getting hotter and hotter quickly like the land does, the water uses a lot of that energy to break the hydrogen bonds holding the water molecules together.
Ah, changing state almost, latent heat.
It's related to latent heat of vaporization, yeah.
Yeah.
It takes a huge amount of energy just to break those bonds, which keeps the water temperature itself from rising dramatically. The land doesn't have that mechanism, so it heats up fast and radiates heat back into the air.
So the ocean acts like a giant heat sink, absorbing energy without its temperature skyrocketing.
Precisely. A huge thermal regulator, or thermal battery, you could say. The energy is conserved, just stored differently.
That's a great explanation. Okay, let's switch gears to the biological side of energy. Primary productivity. This is like nature's accounting department.
Huh. Yeah, you could think of it that way. It's about tracking the energy flow, starting with plants.
Okay, so what's the first number we look at?
First is gross primary productivity, or GPP. That's the grand total. It's the total amount of solar energy that the producer's plants, algae, phytoplankton, capture and convert into chemical energy, usually glucose, through photosynthesis.
So GPP is the total sugar made, the total energy income.
Exactly, the gross revenue. But plants aren't just sitting there making sugar for everyone else. They're alive. They need energy too.
Right, they have to run their own metabolism, grow, repair tissues.
That's right. They use up some of that energy they just captured through cellular respiration. We call that energy cost respiration, R.
Okay, so GPP is the total income, R is the plant's operating costs.
Perfect analogy. And what's left over after you subtract the cost from the income?
The profit.
Exactly. And that profit, in ecological terms, is the net primary productivity, or NPP. That's the energy that's actually available to the next trophic level, the herbivores that eat the plants.
So the formula is key. NPP equals GPPR.
You absolutely need to know that formula. NPP is the energy that supports the rest of the ecosystem. If NPP is low, you just can't support many consumers.
Right. Which brings us to that classic test question, sometimes a bit tricky. Which ecosystem on Earth has the highest overall NPP?
Yeah, this one catches people. Your first thought might go to the places that look the most lush and dense, right?
Like tropical rainforests, maybe estuaries or marshes. They seem packed with life.
And you're right, those ecosystems have the highest NPP per unit area, per square meter. They are incredibly productive because they usually have lots of water, sunlight, and nutrients.
But that's per area. The question is about the overall total for the whole planet.
And the winner there, maybe surprisingly, is the open ocean.
The open ocean. But isn't it kind of like a desert out there, nutrient-wise? Low productivity per area?
It often is quite low per square meter. But think about the sheer size of the open ocean.
It covers most of the planet, like 70%.
Exactly, about 71%.
Yeah.
So even though its productivity is very spread out, very dilute, when you multiply that low rate by that absolutely enormous area, the total amount of energy captured by phytoplankton in the open ocean is greater than any other ecosystem type on Earth.
Scale matters. The total contribution is huge, even if it's not concentrated.
Scale wins the global total for NPP.
Okay, great clarification. So let's circle back now. We've talked about diversity, niches, tolerance, succession, energy flow. Why does all this stuff matter to us, to humans? This gets into ecosystem services.
Right. This is the framework for understanding how much we rely on all these natural processes that we've just been discussing. We often take them for granted, but they provide essential services.
And we categorize them, right? What are the main types?
Yeah, usually into a few groups. First, you have regulating services. These are benefits we get from nature basically regulating environmental conditions.
Like climate regulation.
Exactly. Plants performing photosynthesis, pulling massive amounts of CO2 out of the atmosphere. That's a huge regulating service, helping control climate change and air pollution. Flood control by wetlands is another one.
Okay, regulating. What's next?
Then there are supporting services. These are sort of fundamental processes that are necessary for all the other services to even happen. They're the foundation.
Like soil formation. We talked to how slow that is.
Soil formation is a perfect example. Nutrient cycling, like those nitrogen-fixing bacteria making nitrogen available for plants, that's a critical supporting service. Pollination, pest control by natural predators like bats eating insects. These all support other services, including food production.
Okay, so regulating, supporting. What's the last main type?
The last one is often called cultural services, sometimes includes aesthetic or intrinsic value. These are the non-material benefits we get from ecosystems.
Like just enjoying being in nature.
Yeah, recreation, hiking, spiritual enrichment, aesthetic beauty, that feeling of well-being you get from being outdoors. But it also includes something deeper, maybe harder to quantify.
What's that?
It's that sense of connection, or maybe that feeling of loss, that sort of slight depression or sadness you might feel when you hear about a species going extinct, like the koala example you used earlier.
Even if I live nowhere near Australia and will never see one.
Right. Even if it has no direct impact on your daily life or the regulating services you depend on, there's often still this intrinsic sense that biodiversity matters, that losing a species diminishes the world in some way. That's a cultural or intrinsic value.
That makes sense. Okay, so we've hit a lot of key Unit 2 ground: diversity metrics, island biogeography, niches, tolerance, succession, conservation laws, productivity, and these vital ecosystem services.
A whirlwind tour.
Definitely. Before we wrap up this deep dive, you wanted to share a final thought, something connecting all this ecology back to the human condition, drawing on E.O. Wilson again.
Yeah, it's a powerful, maybe sobering thought from Wilson, the same mind behind island biogeography. Towards the end of his career, reflecting on humanity's place in the biosphere,
Yeah.
he basically concluded that we are, in many ways, a dysfunctional species.
Dysfunctional. How so?
He argued that the core problem lies in a mismatch. We have, essentially, Paleolithic emotions,
Stone Age feelings.
Stone Age feelings,
Yeah.
deep-seated instincts hardwired from our time as hunter-gatherers. Things like tribalism, territoriality, aggression towards perceived threats, wanting to maybe metaphorically or sometimes literally kill the person who cuts you off in traffic.
Okay, those ancient instincts.
But here's the dysfunction. Those ancient emotions are now operating within the framework of medieval institutions, social structures, political systems that haven't always kept pace, and most critically, wielded with godlike technology.
So Stone Age anger combined with 21st century power.
Precisely. We have the technological capacity now to fundamentally alter ecological succession by paving continents, to decimate biodiversity faster than any asteroid, to overwhelm the planet's regulating services with our waste and emissions. We have the power to drop a bomb and kill millions in an instant.
Wow.
Yet our emotional responses, our tribal conflicts, our short-term thinking, they haven't evolved at the same pace as our power. And Wilson saw this profound mismatch, Paleolithic emotions, medieval institutions, godlike technology, as the root cause of so much global conflict, environmental destruction, and the sustainability crisis that really defines much of Unit 2.
So what does this all mean? As you're studying for your test, thinking about niches and tolerance and succession, maybe keep that conflict in mind. The conflict between our ancient evolved human nature and the almost unimaginable technological power we now possess, and how that impacts every ecological principle you're learning.
It adds a layer of urgency, doesn't it?
It certainly does. Think about that as you continue to prepare. Good luck, and that's the deep dive for today.